Alrighty, geometry friends, here we go. We finished chapter 2, and so it's time to do the practice test in this video, and we'll also be doing the chapter 2 review this week. So here's a couple sample problems from the practice test, page 134. You'll be doing 1 through 23 all. And again, these solutions aren't in the back of the book, but they'll be posted along with this assignment as a PDF. Alrighty, let's jump right in. I'm going to be doing problems number 4, 5, 14, 15, 17, and 23. So a nice little representation. So let's look at number 4. Number 4 says find the next term. Oh, actually, no, it's different. It says show that the conjecture all complementary angles are adjacent is false by giving a counterexample. So in other words, it already tells us it's false. We have to draw or give a counterexample because that's how you prove conjecture's false. All complementary angles are adjacent. Okay, well, complementary means that the two angles add up to 90 degrees. Okay. And that they have to be adjacent. That means that the two angles have to be right next to each other, something like this. Typically, that is the case. But notice there's nothing that says that the two angles, it just says that they have to add up to 90 degrees. It doesn't mean that they have to be congruent to each other. So we could draw something like this, where say I've got a series of angles, and I could have this angle here be 70 degrees, and say this angle right here is 20 degrees. All right, and so technically those two angles, the 70-degree and the 20-degree angle, those are complementary because they add up to 90, but they're not adjacent because you can see they're not next to each other. There's this angle here in between them. And so those would be two angles that are complementary, but they are not adjacent. So this would provide us with a counterexample. And so there we go. I'm not going to bother boxing that. It's kind of a big drawing. Okay, number 5. Identify the hypothesis and the conclusion. All right. The show is canceled if it rains. Now, the reason I wanted to do this one is because it's just a typical trap that you could fall into. If you're not thinking, you could quickly, and we're supposed to underline the hypothesis once and the conclusion twice, is you might just quickly go, oh, look, the show is canceled, it rains. Okay, but don't just get caught up in going left to right and assuming that's the correct order. The key is the word if. If is the hypothesis, because that's if this happens, then the conclusion follows. So that's why that would be a mistake. The hypothesis is if it rains, then the show is canceled. And you can syntactically build your sentence different ways to where the hypothesis can come second. So be careful. This is in fact your hypothesis, or as we've learned, it's called P. And over here you have the conclusion, and that is Q. Because if it rains, then the show is canceled. It's not if the show is canceled, then it rained, or then it rains. That would be getting it backwards. All right, so to track the word if, or the word then, because then would be, this one doesn't use then, but then would be the conclusion. Okay, just wanted to point that out. A little tricky. Number 14. This one, we are going to write the conditional statement and the converse. They've given us a biconditional. So Chad will work on Saturday if and only if he gets paid overtime. So there's our key bridge, if and only if, making this a biconditional. So here we go. Chad will work on Saturday is one of our clauses, and then he gets paid overtime is our second one. So for each of the conditional statements, we'll just transition from one to the other. So first, let's go ahead and go with if Chad, and you just have to change the tense a little bit. If Chad works on Saturday, then he will get paid overtime. Okay, good stuff. And then for the converse, we simply reverse that. If Chad gets paid overtime, then he will work on Saturday. And it's worth it to them, I guess. And so we're not really asked, we can't really know if we're going to evaluate this or not, but we're given the biconditional, and you just identify your two clauses and then make sure that it grammatically works out correctly, but then just put it one way and then reverse them and put them the other way. Okay, here we go. Well, we'll keep moving. Can't ask for questions because it's a video. But. All right, number 15. Number 15 says, determine if the biconditional B is the midpoint of AC if and only if AB equals BC. Determine if that is true. If it's true, and if it's false, give it as a counter example. Okay, so B is the midpoint of AC if and only if AB equals BC. So they're picturing a situation here where, let's get the right color. B is the midpoint of AC if and only if AB, so this piece, is congruent to BC. Now you can see, like the example of the adjacent complementary angles we did a minute ago, most of the time, yeah, that works. Like most of the time, complementary angles are adjacent. But as we did up there, we imagined that doesn't always have to be the case. It's often true, especially when we're doing exercises, but it doesn't have to be true. And we run into something similar here. If we say B is the midpoint of AC, it has to divide that. That's true. But here's where you got to be careful, because a biconditional has to be true both ways. So in other words, if I say B is the midpoint of AC, then AB equals BC. That is true. But what if I reversed it and said, if AB is congruent to BC, then B has to be the midpoint of AC? That is not necessarily the case. And that's the key with a biconditional. You have to check the conditional and the converse to make sure it's true both ways. And we could easily see something like this, where I have A, B, C, and I can do that. And in that case, A, B, and BC are still congruent, but you can see that B is not a midpoint because it lies upon two different lines. It's no longer the same line, AC. So just be careful. Make sure if you're being told to evaluate a biconditional, it oftentimes sounds like it only works one way. It sounds like the only thing that matters is it's a midpoint. Remember, it has to work forwards and backwards. So check it both ways and make sure there's not exceptions in either case before you say it's true or not. So this, in fact, would be false because we were able to come up with a counter example. Okay, number 17. Let's see, 17, I think we're solving it. So we're doing algebra, and then we're practicing our proofs by justifying it. Okay, so let's get started. Let's solve it. We got 0.4t plus 3 equals 1.6. Well, first thing, we'd want to get our constants away. So we're going to get 0.4t equals negative, let's see, that would be 2 or 1.4. Negative 1.4. Okay. And then we're going to divide. I usually just solve these before I bother putting any justifications. Divided by 0.4. Okay, I'm going to go ahead and check that. I'm just pulling out my calculator. I actually haven't solved this one yet. So 1.4 divided by 0.4, we get 3.5. So t, canceling there, t equals, and it's a negative 3, negative 3.5. Okay, and just checking to see if I did that one right. Yes, looks good. I'm going to go ahead and box that just because it's a good habit. Now let's go ahead and put in our statement, our reasons. So here's our statements. We separate that from our reasons over here, and we justify each step. So the first equation, where did that come from? That was given to us. We didn't use any theorem or anything to come up with it, because that could be the case, substitution. Then we did this. We got the next thing by subtracting the 3, so that's the subtraction property of equality. And then we got the final solution by dividing by 0.4. So that's the division property of equality. Okay, so pretty straightforward. Practicing giving reasons as you work your way through algebra problems, teaching us how to do proofs. Alrighty, and the last one, 23, a full proof that I've written the given and the prove and provided the picture. It says given angle AFB is congruent to EFD. And so we can see that that's already marked here. AFB is right there. EFD is right there. And so that's what those red marks mean. They actually put that in the drawing for you. So those are congruent. Now we have to prove that FB, so this line here, bisects AFC. So we need to prove that that is right down the middle and cutting AFC in half. Okay, well, let's give that a try. And the clue here is if something bisects AFC, that means that this angle here must be congruent to this angle here if in fact it's being bisected by FB. So let's see if we can get to proving that. But where do we start? If you're not sure, always start with the given. So let's get our given in there. Angle AFB is congruent to angle EFD. And this is why I always tell people on proofs, you never have an excuse for getting a 0 on a proof because you can at least always write the given. Boom, we did that. Okay, so now we know these are congruent, and somehow we have to prove that this angle is congruent to this angle. Well, that means there must be some sort of a clue in the drawing or what they told us. And what I can see right away is we've got vertical angles. I know this angle, and it is vertical with this angle up here because they're on opposite sides of those crossing lines. They're opposite angles. So what we can say is angle EF, oops, if I could write correctly, EFD is congruent to angle BFC by the definition of vertical angles. Actually, no, that would be fine. I wouldn't mark it down for that, but basically, because they are vertical angles. Either one is fine. Let's see, what does the book say? I'll let that be the tie break. Yeah, we'll do definition of vertical angles. Okay, and now I can see that that means these two angles are congruent. So that means, remember what I said earlier, I can now see that AFB is congruent to BFC, which is then going to allow me to prove that BF is actually the midpoint. So let me just go ahead and state that, and we'll be one step away from victory. So in other words, angle BFC is congruent to, oh, kind of lost track. Oh, yeah, angle BFC is congruent to AFB. Okay, and again, so how do I know that? Well, let's see, I can do substitution. If EFD here is congruent to both of these, then I can link these two together. If you remember what that's called the transitive property of equality. Okay, because let me just show it again in blue. But what I did is this was the given, and then this was vertical angles, and I can see that now this provides a link between these two. So now I can go straight from AFB to BFC. Okay, I'm gonna go ahead and let's leave that. And so then that allows me to say then, therefore, BF, yes, BF, ray BF bisects angle AFC because that's the definition of a bisector. Okay, so in other words, sorry, it's not quite fitting on here really well, but I can see if once I prove that these two are congruent by transitive, then I know that this in fact has to be a bisector because it has created these two. It's created these two congruent angles. Okay, and then I can see now my last step here, BF bisects ray. I should fix that. Ray BF bisects angle AFC. That is the proof right here. So once you get to that, that means you've actually finished the proof because you've proven what they asked you to prove. So again, just looking at it, we had the given, then we were able to notice the vertical angles, and then that allowed us to use transitive to prove that the two adjacent angles here and here are in fact congruent. And that of course, is then the definition of the bisector. All right, again, don't be afraid, watch that again, or just practice those proofs. We'll be doing them in the next couple chapters, and if you don't give up, you'll get really good at them. All righty, there'll be a chapter 2 review that for further practice, but otherwise, please reach out if you have questions, because we really want you to have success on this week's celebration for chapter 2.